about his generalized porous media model.
Thank you for the introduction. I'm going to present a generalization of this porous media model. Well, is a well-known symmetric exclusion process. So let me first just describe the context. The fundamental question in statistical physics is to describe the collective behavior of a very large number of interacting agents. So underlying to this collective behavior, there's a dynamics. I'm going to focus on exclusion symmetric one-dimensional processes in a discrete finite lattice. So let me just fix here the context with an example. So this process here is called the symmetric simple exclusion process, and you fix a finite lattice. On each side, you put either a particle or leave it empty, and the dynamics evolve by nearest neighbor jumps. So a particle can jump to its neighboring site if this site is if the site is occupied is empty. Otherwise, nothing happens. And if the site is empty, it jumps with rate 1. Now, this description of the collective behavior, the one that we are going to focus on is on hydrodynamic limits. So in this sense, if we take some local average of particles in this very large system, and then we perform a space and time rescaling, what we obtain is that this local density behaves as the solution of some PDE. In this case, it's the heat equation, and the PDE is with different formulations, either classical or weak formulations. You can have fractional operators, you can have different equations with different dynamics, and so on. But in this case, we are going to focus on something simple as this. Now, the symmetric part is because a jump to the right happens with the same rate as a jump to the left, as long as the neighboring site is empty. The exclusion name, simple exclusion name, is because we can have at most one particle per site. And so this is our main setup. This process is a Markov process, so each jump happens at a time and depends only on the previous configuration. And the lattice will be taken to be very, very large and rescaled into some continuous thing that we associate with the macroscopic space. In this thing here, we associate this discrete space. In discrete dynamics, we associate with the microscopic space. Now, in order to fix some notation, we will consider the one-dimensional discrete torus. So we take this n very large and identify it with 0. Our state space will be called this omega n. So we have these strings of zeros and ones. The value 1 is associated with the presence of a particle, and the value 0 associated with its vacancy. We write eta has the configurations in this space, and eta x has the occupation at the site x. So the projection of the configuration in this site x in the torus. And naturally, this is belongs to either 0 or 1. This Markov process can be described, it is defined by its Markov generator, that you write it has this, and applied to functions in our state space, it has this expression here. So let me just explain the important quantities here. So this A is the exclusion constraint. So a jump can happen to the right if this site is empty. So here we have, for instance, eta x and 1 minus eta x plus 1. If eta x is occupied and eta x plus 1 is empty, a jump can happen. And by symmetry, the reverse. If the site x is empty and the site x plus 1 is occupied, a particle can jump from x plus 1 to x. This C here, which in the case of the SEP is 1, is a kinetic constraint. So it's any non-negative function that depends on the local configuration. In this case, for the SEP, it doesn't matter the configuration around the node where a jump is going to happen, but if it did, this will take a different value. And this notation here is just the exchange of the occupation value of the site x and of the site x plus 1. So we have just this expression here. What differs then between models and there's another property here I'm supposed to mention. Also, another property from this model is the gradient property. So this technical property here tells us that the microscopic current can be expressed as the gradient of some other function. In more mathematical terms, what we have is that this minus the current here, which is by definition since the process is symmetric, we have this expression. And now this constraint here pops up, and we have this discrete gradient, the occupation variables. And if this quantity is itself the gradient of some other function, we say the model has the gradient property, or is a gradient model. You can see here that because we have this constraint C multiplied by this gradient, if we know the invariant measures and so on, then we can identify this constraint as the expectation. We can identify the diffusion coefficient of the underlying PDE as the expectation of this constraint here. What I mean by that is that if we know the invariant measure of the process, and we can compute the expectation of this guy here, in principle, we know what the PDE should look like. And well, this is the main important properties that we are going to develop here. Now, this takes us to another motivation, but another underlying process. So regarding the description, collective description, we were first interested in studying this equation here. So by that, I mean, we want to have some underlying model where if we take a local average of the particles and rescale the time by this factor here, theta n, and rescale space by 1 over n, where n is the length of our lattice, then this random measure here converges in some sense to this absolutely continuous measure, where this rho, this density here, is solution to this PDE here. So back in around the middle of my dissertation, I started studying this equation here in the Porous Media Model. And well, what we found out in the literature was that one can derive this target equation for different values of m with different models. For m larger than 1, this equation takes the name of the Porous Media Equation, and we have a collection of models that are associated with this equation here for the exponent to be any positive integer. For m equals 1, we get the heat equation, and I just explain the SEP. And for m smaller than 1, this becomes a fast diffusion. And there is in the literature transformation of the zero range, not transformation, a rescaling of the zero range process with some particular initial conditions. And one can prove the hydrodynamic limit and obtain that it is associated with the fast diffusion equation for m equals -1. So a natural question that rose back then was if we can, whether we can construct a model to obtain the slow diffusion equation, the Porous Media Equation in the slow diffusion regime for non-integer values of m. And if we could do that, if we could also construct an underlying family of models that explains the transition between slow and fast diffusion, so m larger or smaller than 1, from a single family, not different types of models here. Because the porous media has kinetic constraints that C is different than 1, the SEP does not, and the zero range can have more particles, more than 1 particle per site. So we want a single family, and we want to extend this to non-integer stuff. So yeah. So that was the main goal back then. And so to explain what we did with these things, I should explain first the Porous Media Model. That was going to be also a basis for all the rest of the models that I'm going to present. So the Porous Media Model constraints can be explained like this. We fix some n. For instance, if we fix n equals 1, we expect to obtain this diffusion rho. And the constraints are, we ask for a particle in the left, or a particle in the right, where a jump is going to happen. So suppose a jump is going to happen in between in the node 0 and 1. If we have -1 occupied, we add 1 to the rate. If we have 2 occupied, we add another 1 to the rate. This is generalized for larger values of n in this way. So we consider a window of length n. In this case, n is 2. Around the node where a jump can happen. So in this case, for n equals 2, we have this window in the left, this with 1 particle in the left and the right, and this whole window in the right. For each fully occupied window, we add a +1 to the rate. So in the end, the rate will be the number of fully occupied windows of length n around the node. And well, this is the constraint for n equals 1 and n equals 2. In general, you have this formula here for the constraint. I omitted here the x and x plus 1 because the constraint will be the same for each site. So we just define the constraint in 0 and 1 and translate it to some site x. So we have this summation over j here, where the windows are indexed in j, and this product of occupation variables, which is just the product of the occupation in these windows here. So if this is 1, then the whole window is occupied, and then we move on to next windows, adding the rate. And well, just notation also what I mentioned of translating these constraints. We just define here this translation operator, and then we apply this translation operator to the constraints in 0 and 1, and voila. This model has some very nice properties. It has blocked configurations. So by that, I mean that there are configurations where we can see no evolution of the system. And of course, this is true because we ask for at least n particles around the node, aligned particles around the node. So we can always hook up some configuration with where each particle is at a distance larger than n. And in this case, every rate will be, the rate associated to every node will be 0. It is also a gradient model. And also satisfies this monotony property here. So the rescaled sequence of these constraints is non-increasing. And by that, I mean that since this constraint C is associated with this diffusion coefficient, then if we normalize this by n plus 1, we should get something which is associated with this rho to the power of n, and this is non-increasing in n macroscopically. So we prove the same microscopically, more or less fixing that this model is models very well this diffusion coefficient here. Okay, now that we know this, how to construct these exponential diffusions, back to the first problem, we wanted to extend the exponent to m non-integer. And the solution that we came up with was this expansion here. So we just consider the generalized binomial theorem to expand this diffusion coefficient, and we get a series. And so because we know how to model rho to the power of n, if we flip the occupation value of each site, so we change particles by holes and holes by particles, we should be able to model 1 minus rho to the power of n. And then if we take linear combination of these processes, we should get something that looks like this. So what I mean by that is this, we guess this constraint here. Now these binomial coefficients, because m is non-integer, they change sign depending on the value of n. So it's not obvious that this constraint is well-defined. And in fact, it is well-defined only if m is between 0 and 2. But as a solution to our first problem of describing this transition between slow and fast diffusion, so this model works very well because we can get the transition range here. When m equals 1, we get the heat equation. M equals 2, we should get the Porous Media Equation. And m closer to 0, we get faster and faster diffusion. And in fact, we have this interpolation property in with these rates here. So if we take the limit m to 2, we get the Porous Media model. And if we take the limit m to 1, we get just 1, so we get the 7. Now, contrarily to the Porous Media model constraints, this is not very nice to interpret. It's just a mathematical object that serves our purposes. But we can visualize the constraints in order to have some better feeling of the dynamics. And this is achieved in a particular quotient space. Quotient space. So because the Porous Media models, let me just go back here a little. Because the Porous Media models ask for these fully occupied windows, if we know where the first empty site is to the left of 0 or to the right of 1, then we know the value, the occupation value of all of these windows here. So we just need to parameterize by the first empty site to the left and the empty sites to the right, and we can get the whole picture of the rates. Now, in this case here, we have the flipped process. So we need to look at the first particle instead of the first whole. And if we do that, and let's just write minus x0, the particle to the left of 0, and x1, the particle to the right of 1, what we get is these pictures here for the values of the rates depending on m. So you can probably cannot read, but the x-axis here is x1, so the particle to the right, and the y-axis is x0, so the particle to the left. And for m equals 1, as I said, we get the SEP, so we have the constraint equals 1 everywhere. For m equals 2, we get the Porous Media Model 2, so the flipped Porous Media Model 2, so the constraints now are on the holes, not on the particles. And so if the first one is at the site 2, and the first one to the right is at 2, and the first one to the left, then we have the Porous Media Model rate will be 2. So we are in this case here. So first to the left, first to the right, each of them sum to 1. If we have only one, either in the left or in the right, then we get 1 as a rate, and otherwise we have 0. And so our interpolating process models this transition, models continuously this movement here from m equals 2 to m equals 1, where we get faster and faster, larger and larger rates, so faster and faster diffusion. And as m goes from 1 to 0, we get this very fast diffusion. And in particular, the model is irreducible. And well, that's basically it. So we start from this constant diffusion here, and we get larger and larger values in general, but depending on where the first hole is, very large values. And because we have this m multiplying, here, when m is 0, this will be 0, so we get at some point something that should approach 0. Okay, so that's it for motivation. So what we have for this model here is the hydrodynamic limit. More or less vaguely, what we prove is that this local average here converges in probability to this absolutely continuous measure, where this density is a weak formulation, is a weak solution of this Porous Media equation here. We did this using the entropy method. There are some technical difficulties here and there, because depending on the value of m, so if we are on the fast diffusion scenario, the rates can explode as the system goes to infinity. So there are some delicate arguments in order to compensate that with the coefficients that appear on the series. But in the end of the day, we were able to prove this. And what's important is that we were able to identify the main technical issues that we have when proving this type of results, when the constraint follows this series-like term. So there are some quantities that we want to estimate very well in order to treat models that have this, that look like this here. So yes, that's what we got from this project. Now, the next step for this is, so there are a couple of motivations for the model I'm going to present now, but the first one is that we just saw that we can construct models for the target diffusion coefficients, and this diffusion coefficient can be expressed in terms of a series. So we can ask what types of diffusion coefficients can be obtained in this way. So starting from gradient symmetric exclusion processes, what is the class of functions that can be expressed as the diffusion coefficient of some underlying gradient model? And another motivation is that we have the previous process only works up to m equals 2. For m larger than 2, we are going to need the tools that we are going to present now. But all of this to get some model that should behave as to get some model that on the limit we get some target diffusion coefficients, and if we can construct some underlying gradient model that behaves like the Bernstein polynomial basis, then in principle we might be able to get all the class of continuous functions in compact support. So the first step here is to define this Bernstein polynomial basis in the context of gradient models. And then we can apply all the tools that we got from the previous works to get continuous functions as diffusion coefficients. So just a reminder, there is also an interest in getting some model for this diffusion here, which there isn't in the literature, there wasn't in the literature, because this diffusion, so depending on the values of the density, we have no diffusion. If we have very low density or very high density, we get in general no diffusion. But for the porous media model, we get no diffusion only for low densities. And in particular, the optimal diffusion will be when the system is when we have a lot of particles, so we have a very large density. But for this Bernstein basis here, we get an optimal diffusion, which is, in fact, when rho is n over n plus k. So there is an interesting to getting a model for this, besides the more technical motivation. So how was our approach to model that? So first thing, it should be mentioned that we cannot simply develop this power 1 minus rho over k, develop this using the binomial theorem, and then get a polynomial in rho and modeling each row by porous media models. We cannot do that because in the end, the model will have possible negative rates. So we cannot develop this and apply the same argument as before. We need to model this as it is. So our approach was to first start from the porous media model. We consider these windows, but with length n plus k. And then we choose which sites on each of those windows we should change the constraints to having particles to holes. So we are looking at a window of length n plus k, and then we want to say, okay, so if I ask for k holes inside these windows, will I get a gradient model? And how can I get this idea working on? So what we did was to each position of the k holes inside this window of the porous media model, we add a non-negative weight, and we flip the occupation of these sites. So what we are considering here is more or less has a distribution inside each of these porous media model windows, and this distribution tells us how the empty sites will be located inside those windows. So we have this sum over I. This I is just all the subsets with n elements of the window. So where we are going to put with k elements of the window, where we are going to put the particles. This P here is what we are going to flip, particles by holes. So we are going to flip, oh, there's a typo, it's supposed to be a K here. We are going to flip K, guys. And this notation here is just that we are flipping K and looking at this porous media model window here. So yeah, that's the prototype model. We want to get the values of these coefficients here, or the distribution inside this window, such that the underlying model is a gradient model. Okay, so let me just present for a very simple case our strategy. So the first step, so we have this prototype model here. We have these porous media model windows. We start from the window in the right, site 2, 3, and move to the left. So 2, 3, minus 1, 2, and then minus 2, 1. If we have, since we want n and k equals 1, we need to flip just one occupation, but we don't know which one it is. So for each of the windows, we flip whatever we have. So we first flip the site 2, and then we flip the site 3, and with each flip, we have a different weight. Then we develop these products here, because this eta bar is 1 minus eta, so we can develop all these and group all the terms. In the development of this, we will have terms with one occupation variable and terms with 2 occupation variables. The terms with the 2 occupation variables will then be all of these windows here. So what I mean by all of this is the following. We develop these guys. Once we develop, we get some terms which are in common, and so we group the coefficients. The term that has all the occupation variables will be this guy here. and this is the porous media model. We just group the terms and we get the porous media model windows. And because the sum of the weights is 1, as I mentioned with the interpretation of the probability distribution inside each window, we get that this last line here is the gradient of some quantity. But these two lines here, we need to look at it carefully. So what we see is that have here in different colors. So in red, the terms in red are translation of the terms, are translations of each other. So the terms here in the left, we have the plus sign. This we have the minus sign. This minus sign comes from the gradient. Here we have eta 1 minus eta 0. So these guys will all be associated with eta 0 and this guy with eta 1. And if the plus guys are all translations of the minus guys, then what we get is a linear system. What we get is a linear system for these weights here that characterizes the gradient property. So specifically what I mean is, if we translate this to this, and we can do that by just summing and subtracting eta minus 2, eta 0 to this, and we go and see the operators that are here. So we have the eta 1 minus eta 1, eta 3 minus a translation of eta 1 and eta 3. So we have a gradient inside here. And in the end, what we get performing this for all of these terms is this linear system here. If we solve this linear system, solving this linear system gives then the weights so that this model is ready. Now, doing this in general is the same idea, but it's much more demanding, because here we are really looking at the sets, so these sets here. To do this in a more general way, we should add some other language to this approach here. We consider some equivalence classes of these sets. Then we consider equivalence classes in the indexes of these weights here, because once we develop these guys, we need to keep track of all of the weights that were grouped. Then we need equivalence classes of these sets here, and so on. So it's a little bit more technical, but the important thing is that in the end of the day, what we get is a linear system that looks like this, in the sense that in the left-hand side, we have the same number of terms as in the right-hand side. So a particular solution is always the uniform solution. The uniform solution in this case here is 1 over n plus k, choose k. So from all the sides in the window, I choose k to flip. And in that case, the system will be satisfied. So with this strategy here, we arrive at a very simple model right here. So for a jump to happen between the site 4 and 5, we look at the porous media model windows around this node here. In this case, we have n and k equals 2, so the window will be of length n plus k, and the total rate will be the proportion of windows that we have with exactly n particles. So we start with something that looks a bit messy, but in the end we get something very simple. Well, that's the main model. In this case here we have these windows of length 4, and only on these two windows here we have exactly 2 particles. So the rate for a jump in this node will be 2 over 5. Now let me just write this explain this in more mathematical fashion. So the precise constraint that we defined was this constraint here. And so what we are doing is, for a jump to occur between the sites 0 and 1, we look at the windows of the look at the porous media model windows. We have n plus k plus 1 of them, and if the density in this window is n over n plus k, it contributes 1 to the rate. Then we take this average over all the windows, and we have our final constraint. Naturally, if we have that k is 0, so we have just this exponent here, then what we are asking is for the porous media model windows to be completely full, and so we are back to the porous media model that I introduced previously. So this model here interpolates the porous media model in that sense. It is also a gradient model by definition. What is not very nice is the expression of the function that appears here in the gradient property. Because to do this in general, we need a lot of different objects and equivalent classes and so on. One can expect that this function is very messy, very difficult to work with. And part of this project was to just simplify the function that we obtain in a way that we can work with it. This model also has block configuration clusters. Now, block configurations is also trivial because we need a density.
Sorry, Gabriel, can I ask a question?
Yeah.
So you chose to essentially get a uniform repartition for your coefficients Aij. Would it not have been a simpler model to choose as many to be 0 as possible and just keep a few of them as 1?
Yeah, it looks simple, but we have many possibilities to put the weights to be 0, right? If we have this in this simple case here, we can do that, but in general, we do not know which sites or which classes of sites we want to put the weight to be 0, and we do not know how many. So we need to start from somewhere, right? We do not know how to treat, so we do not know which gradient model has the most number of zeros in these weights here. So in the end, we had to choose which are 0 and then repeat the procedure and check. And then if it doesn't work, choose another one, repeat the procedure and so on. It was easier to consider with no zeros at all. And then if we want add zeros, then to start with a bunch of zeros and then add different than zeros.
Okay.
And again, all of this, we can do this by hand for very small values of n and k. But for very large, and even for n and k equals both 2, it's a bunch of computations because we have from these windows, we need every possible configuration within these windows to have a different weight. So we have a very, very large system with very small values of n and k. So picking which of them are 0, it becomes intractable. Yeah, and okay, so we also have these mobile clusters. I should have written here what this means, but okay, so as I mentioned, mobile clusters are groups, clusters of particles that can be seen as a single particle. By that I mean that, for instance, this black square here is a group of particles, it is a mobile cluster, and this dot here is a particle. So we can have this transition here, can move this cluster in this site, and the same with the empty sites. Now the mobile clusters for this model here are composed by this thing. So this white square is just a window with exactly n particles. This white dot is an empty site, and this is a particle. Now this whole cluster we can have these transitions here with particles and holes. And the reason is that because we have n particles in this cluster, in this square here, then we can always have a jump from this side to the other side. And in particular, we can also reorganize this whole cluster here, because if we want to reorganize the particles inside this cluster, then we need a jump. So we remove a pair of a particle and a hole, and this particle and hole outside compensates for that. So we can reorganize this cluster as well as we please. And for that reason, we can have these transitions here. As I mentioned, this model also interpolates the porous media model. When we have no particles here, we get the porous media model. It has the symmetry property. So if we exchange the particles and hole, this is the same as exchanging n and k. And it also satisfies this partition of the unity property here, which tells us that the generator of the SEP can be expressed as the superposition of these B models here. In terms of the rates, this tells us that if we sum the rates of these models here, then we get 1. Okay. So, okay, now we have a basis. We can construct this polynomial to approximate in principle any continuous function, but it's also curious to see that this basis is also expressed in terms of another underlying porous media basis. So I mentioned that we cannot develop this product here and then model the resulting polynomial in rho by porous media models, because what we get is something that has possible negative rates. So we constructed this from the ground. But once we constructed this, we can identify an underlying basis. So precisely what we have is this thing here. So we have these P constraints here that we wanted to fix as the porous media model constraints, but in this case here, they have a different phase. So this constraint here tells us that for a jump to occur between the sites 0 and 1, we need at least L. Okay, so first, we fix some range capital L. This range here will be the length of each of the porous media model window. So we have 2L as a range. And then we ask for inside each of these windows to have at least L particles. If we have L particles inside each of these windows, inside one of these windows, then we also have this weight here, this probability weight here, that is just from the number of particles that we have. We choose L over the whole sides of the window, we choose L. So we have this probability here associated with the constraint. And in particular, this constraint here, one can show that in the limit is associated with the diffusion coefficient rho to the power of L. So in this case here, rho to the power of n plus L. So yes, this collection over small l, fixed capital L, and the collection over small l is an alternative to the porous media model, in the sense that we can use this as a basis to construct this diffusion here. But we didn't see it from the start, of course. We just constructed this diffusion and then identified the basis, but that's that. And so it's also surprising that it is interpretable in a nice way. It's not very complicated to work with. Okay, so just to conclude some properties about the model, I mentioned that the gradient property. So sorry, here. So the gradient property has these functions here, which in principle are very ugly functions because they depend on a lot of objects. But we can simplify this a lot once we identify this basis here. And so we just need to find the function associated with the gradient property for this constraint here. If we find the function associated to it, then we take a linear combination and we have the original one. And it turns out that with some combinatorial approach, we can express this in a nice way. So this satisfies the gradient property, where this h function is composed by 3 terms. We have this term here, which is the dominating term, and it will give the exponent that we want, exponential that we want. We have this gradient term here and this f term. Because of this gradient, we can see that this whole thing here is a remainder term that will not be seen in the scaling limit. And this guy here, one can study it and show that it is also absent in the scaling limit. So yeah, these are all error terms here. And their expression are much nicer than what we originally get from the B model. So we have this expression for the G function here. We have simple objects. We have this SA. So we have this summation over all the parts of this window here with L elements. So we pick L from this set. We have this coefficient SA, which tells us so how more or less how much space this set occupies in the fixed window of length capital L. So if the maximum is large, then this is small. If the maximum is small, this is large. And we center it around this particular value here. And then we have more products of occupation variables. So we have a simple expression for this G here, although what's really important is that it is bounded, because this gradient here takes care of the rest. And for this f function, we have another expression, not so simple, but much simpler than previously. So we have first this term here. I think I didn't write this down. Yeah, okay, sorry. So as we have this p rate, we have this sum over j, and I'm calling pj these terms here. So what we have is something that appears on the constraint. You have almost the gradient property here again. If we had the summation over j, we will get again the gradient property. And then we have this extra error term here. And this is absent in the scaling limit because we can exchange the occupation of this site, of the site A with the site Y. But in the end of the day, what's really important here is that we have a difference inside this product, which is enough to show that this vanishes in the limit. And for this guy here, we have a gradient. And so we only, so we have this dominating term here, which should go to rho to the power of L minus L plus 1. And so we plug in this inside our expression for the gradient property for this guy here. And so what we get is this a linear combination of these h functions here. Okay, so yeah, up to this point we have a nice interpretable model for this diffusion coefficient, and we have a nice expression for the function appearing in the gradient property. So we have more or less all we need to prove the hydrodynamic limit for the underlying process. And well, I think wasting time. So this is what we have for this process and what we are working on at the moment. So one can also define some open boundary conditions associated with this and prove also the hydrodynamic limit. The hydrodynamic limit for both the open boundary and for in the torus case is, so what we have is that the hydrodynamic equation is this equation here, where so we have this generalized Porous Media Equation, where this B function is incomplete beta function, which is just a primitive of the diffusion coefficient, but it has a name. Also, we prove this with the entropy method. The process is irreducible, so we added a small perturbation in order to get this. There are some technical difficulties here and there in the proof. Namely, for the two blocks estimate, we need new arguments because the arguments for the porous media models only allow us to have some cutoff of low densities, and in this case, we have no diffusion whenever we have low and high densities. So we need a cutoff both in low densities and high densities, and the tools for the porous media models didn't work to have this simultaneous cutoff. So we extended that a little bit, but in the end of the day, we can get this hydrodynamic equation. So this justifies that the model works. So it gives what we ask for. And we can also couple boundary conditions, getting the usual triplet of boundary conditions, Norman and Robin and Dirichlet. One can also extend this dynamics to a long-range dynamics. This is a bit non-trivial because it's not clear how we can extend the nearest neighbor dynamics to a long range, maintaining the gradient property. There are an example in the literature for the porous media model, but their approach doesn't work, so we extend it in another way. But in the end, we could also prove the hydrodynamic limits for a linear combination of long-range models. And in the end, what we get is that we can exchange this classical Laplacian here by a fractional Laplacian. And again, there are some technical arguments here and there, but we managed to do this. What's still open is to derive the complete range for the porous media equation. So now that we have a basis, we have a model, but there are some technical issues here and there also, and this is still open. And the main goal, so now that we have a basis in principle, we can consider any types of series with enough regularity, enough growth conditions, has diffusion coefficients of the hydrodynamic equation. So yeah, this is it for now, and thank you. And I also have some the references for these works. They are not on archive yet. They will be very, very soon. The basis is already done, and the rest I'm still revising stuff. But yeah, that's it.
Thank you, Gabriel. Are there any questions? I have one. So oh, sorry. Go ahead.
So in these models that you obtain when you want to approximate a given diffusion coefficient by these dynamics, under which conditions these models are attractive?
Oh, I'm pretty sure none. But I cannot tell you for sure. Yeah, because since they depend on depend on these local configurations, I'm pretty sure they won't be in general attractive. But I need to check.
And another question. So for functions functions defined on interval 0, 1, there is a similar theory of integral transforms, no, like Laplace transforms. So in principle, you could approximate, maybe not uniformly, but in some way, functions which are not necessarily continuous. So
Yeah.
I don't know if you thought about it, because in that case, the hydrodynamic, the corresponding parabolic equations will have some particular features, no, like
I see.
like Stefan problem and things like that.
But I haven't thought about non-continuous function. I mean, starting from the simplest case possible, but it is very interesting because I have no idea specifically of the technicalities. Yeah, but for now, we are looking at continuous function only because of the Bernstein basis. But yeah.
So you have the hydrodynamic limit essentially for any given diffusive equation. Do you know if your model is suitable to get I don't know, the CLT, the non-equilibrium fluctuations, the large deviations, and so on?
So
do you see, my question is, do you see like obvious technical hurdles to prove this kind of results?
Yeah, no, there are obvious stuff. So the first problem is that we do not know much about the porous media model either. So fluctuations and large deviations and so on, it's difficult for the porous media model. So in principle, we will have the same difficulties as we have for the porous media model, which comes from the irreducibility, most of it. But then we also have the difficulties coming from the series expansion. So what I mean by that is, that extra to the porous media model difficulties, we need to treat all the porous media models at once. So we need some estimates on the coefficients that we are going to have. So this depends on the function. And then we will also need, it's not here in the slides, but we also need the average rate in the whole torus, and we also need the tails of the function, and so more technical properties of the function and the porous media model. So in the end of the day, the difficulties come from both the lack of irreducibility and that the estimates that we need are not easy to obtain at all. So yeah. But in principle, we should obtain a set of functions such that it is as difficult as the Porous Media Model.
So looking at this expression, I got, I have another question.
Yes.
Okay. So in principle, if you take the integral infinite line, okay, so you take your model on Z, it could make sense to consider as the interaction with this infinite sum.
Yeah, yeah.
So do you know if those models will exist, will be well defined? Because it's not clear that
Okay.
you can define it, no?
So in principle, it should be well defined, but it will not be a real sum to infinity, because all the if we are considering Z, all the functions will have to ask for the tails to be light enough, or for the function to have some finite domain or such. So this summation here in infinity will kind of be annihilated by the test functions that we put in the equation. But the model is well defined with the sum to infinity. But in the end of the day, it will be more or less like having an ln here than infinity. But what's so maybe it's relevant here, but this L can grow as we please. So it has no constraints on its explosion. So this is something that can be useful for analyzing in the whole Z. But regarding this being truncated or not, I think the model should be well defined, but in practice, it should be the same as this.
Any other questions? Okay, if not, let us thank Gabriel again.
Thank you.
And we'll see each other on next Wednesday.
Bye.
Bye.
Bye, everyone.